in a coil of wire when a magnet was moved through it, another coil of wire was moved near it, and current was sent through another coil placed near it. In all these cases, there was one thing in common. Can you reason it out? In the first case, the moving magnet changed the magnetic flux of the coil. In the second case, the moving coil, second coil, changed the magnetic flux of the first coil. In the third case, current in the second coil changed the magnetic flux in the first coil. Hence, the changing magnetic flux produced an electromotive force in the coil. Also, if we moved the magnet at a greater speed, the galvanometer showed a greater deflection. This means a faster changing magnetic flux produced a greater electromotive force. Let us delve a bit deeper into this process. Consider the case with the coils and the tap key. When we press the tap key, the magnetic field associated with coil C1 increases from 0 to maximum value. This increases the magnetic flux in coil C2. This increase in magnetic flux in coil C2 induces an EMF in coil C2. If we continually keep the tap key pressed, current in the coil C1 will be constant. That is, magnetic flux in C1 will not change. Hence, the current in coil C2 will drop to 0. When we release the tap key, current in coil C1 decreases from maximum value to 0. This decreases the magnetic flux in coil C2 and induces an EMF in coil C2. This visual also illustrates the effect of induced EMF in a two-coil system. Hence, we can conclude that the induced EMF depends upon the rate of change of magnetic flux. This is Faraday's law of electromagnetic induction. In other words, induced EMF is proportional to the rate of change of magnetic flux. Mathematically, the law is expressed by the equation epsilon equals minus d phi b by dt. The negative sign indicates the direction of EMF, about which we will discuss later in the next section. If the coil has n turns, all of them closely wound, sized and oriented in the same way, then for this coil, epsilon equals minus nd phi b by dt. AC generator. In the previous section, we saw how EMF can be induced in a coil by changing its orientation in an external magnetic field in which the coil is immersed. This fact is used in AC generators. Let us see how this device, an important application of electromagnetic induction, works. An AC generator consists of a coil which is free to move inside an external magnetic field. This coil can be made to rotate by some external mechanism, like a turbine that rotates in flowing water. But the axis of rotation of the coil has to be at right angles to the magnetic field. The ends of the armature are connected to an external circuit by means of slip rings and carbon brushes. Now let us try and understand the working of the AC generator. Consider the movable coil PQRS as shown in the figure. Initially, the plane of the coil is perpendicular to the magnetic field. At this instant, omega t equals 0, and hence E0 sine omega t equals 0. As the movement of the coil starts, PQ proceeds downwards and SR proceeds upward. Applying Fleming's left-hand rule, the direction of the induced EMF in arm PQ of the generator comes out to be from P to Q. And that in SR turns out to be from R to S. Hence, the current flows in the direction PQRS. As the plane of the coil becomes parallel to the magnetic field, omega t becomes 90 degrees. Hence, E0 sine omega t equals E0 sine 90 equals E0. Hence, the EMF induced is the maximum. From here onwards, as the coil rotates, PQ progresses downwards and SR continues to move upwards. Hence, the direction of the induced EMF is still the same, that is, PQRS. But here, omega t goes beyond 90 degrees, and sine is a decreasing function between 90 degrees and 180 degrees. Hence, the value of E decreases. Once the coil aligns itself perpendicularly to the magnetic field, omega t becomes 180, and sine 180 degrees equals 0, hence E equals 0. As the rotation continues, now PQ moves upwards and SR moves downwards. The direction of the induced EMF, according to Fleming's left-hand rule, turns out to be from Q to P in arm PQ, and from S to R in the arm SR. Hence, current will move from SRQP. Note that this direction of current is exactly the opposite of what it was initially, that is, PQRS. As WT goes beyond 180 degrees, the value of E decreases further, since sine is a decreasing function between 180 and 270 degrees. The coil continues its motion and omega t becomes 270 degrees, where sine omega t equals -1. Here, the EMF induced reaches its negative peak. The coil is parallel to the magnetic field at this instant. From here onwards, the coil again comes back to its original position, when omega t equals 360 degrees. The direction of the induced EMF still remains the same, as the motion of the arms PQ and SR does not change. This cycle repeats itself. Hence, we get a variable current which changes its polarity after every half rotation. In the previous section, we saw how an external magnetic field can pave the way for torque to act on parts of a conductor so that the conductor can rotate. This principle is used in several devices. One such device is the moving coil galvanometer, MCG. MCG is used basically to measure small currents and voltages. The visual shows a galvanometer that can read currents in the range 0 to 25 milliamperes in both directions. Note that the scale is center 0. The galvanometer consists of a rectangular coil of wire wound over a cylindrical soft iron core, which is placed in between the poles of a permanent magnet attached to the coil. There is a spring attached to the pointer. The pointer moves over a calibrated center 0 scale. When current is passed through the coil, it interacts with the external magnetic field provided by the magnet. This generates a torque tau equal to N times I times A times B. This magnetic torque tends to rotate the coil. Simultaneously, the spring provides a torque K times phi in the opposite direction such that an equilibrium is reached with a steady angular deflection phi of the needle. In other words, K times phi is equal to N times I times A times B, where K is the restoring torque per unit twist. Hence, phi is equal to N times I times A times B divided by K is equal to I times N times A times B divided by K. For any given galvanometer, the ratio of N times A times B to K is a constant. This deflection is shown by the pointer on the scale. The direction of deflection depends upon the direction of current. That is why moving coil galvanometers consist of center zero scales. There are many ways in which a galvanometer can be used. We have used a galvanometer in a Wheatstone's bridge to find the null point. The device is used in low current circuits to find out whether current flows in them. A galvanometer cannot be used to measure current in circuits directly for two reasons. The instrument is very sensitive and can read only in mu times A. As the instrument has a large resistance, when connected in series, it will alter the current flowing in the circuit. In order to solve the problem, a resistance known as shunt resistance is connected in parallel to the galvanometer so that most current will flow through the shunt, which otherwise would flow through the galvanometer. The circuit diagram for connecting shunt resistance to a galvanometer is illustrated in the schematic diagram. The effective resistance of this shunt arrangement is Rg times Rs divided by Rg plus Rs is equal to Rs if Rg is larger than Rs. Larger is the shunt resistance, higher the use of shunt in this situation. The scale of the galvanometer is such that it is easy to read the current. For this, manufacturers consider an important parameter known as current sensitivity. Current sensitivity of any current measuring instrument is the deflection per unit current. We already know that phi divided by I is equal to N times A times B divided by K. Thus, this is the current sensitivity of the galvanometer. Galvanometer manufacturers consider this quantity as very important and increase the current sensitivity of their product by increasing the number of turns. Different galvanometers come with their own current sensitivity. By connecting the galvanometer parallelly in a circuit, we can use it as a voltmeter to measure small voltages as shown in this visual. Note that the scale is center zero and can read voltages in both directions, from 0 to 10 volts. When it is used as a voltmeter, it is important to send a very small current through it. Otherwise, the original setup will be disturbed. We can send small current through the device by using a large resistance R connected in series with the galvanometer as illustrated in the schematic diagram. In this situation, the voltmeter resistance is equal to Rg plus R, which approximately equals R. In designing devices used to measure voltages, a parameter known as voltage sensitivity is commonly used. Voltage sensitivity is the deflection per unit voltage is equal to phi divided by V. For the galvanometer, we know that phi is equal to I times N times A times B divided by K. Therefore, voltage sensitivity phi divided by V is equal to the product of the ratios N times A times B to K and inverse V, which is equal to the product of the ratio N times A times B to K and the ratio I to R. It looks as though if we increase current sensitivity of a galvanometer, its voltage sensitivity may increase and vice versa. But in practice, it is not so. Let us see the reason. In the equation for current sensitivity, phi divided by I is equal to N times A times B divided by K. If we double the number of turns, then the current sensitivity is equal to twice N times A times B divided by K, which is equal to twice phi divided by I. Of course, the current sensitivity seems to be double. But when we double N, the resistance R also doubles, as resistance is directly proportional to length. We know that phi divided by V is equal to the product of the ratio N times A times B to K and inverse V, which is equal to the ratio N times A times B to K multiplied by inverse R. When N tends to 2N, R tends to 2R. If we substitute the doubled values of N and R in the equation, we see that the ratio phi to V remains unchanged. Thus, modifying a galvanometer into an ammeter is different from has two coils known as windings, electrically insulated from each other but wound on an iron core. Usually the core is square or donut-shaped. Alternating current is passed through the first coil, known as primary coil. This generates a magnetic field, which in turn induces a current in the second coil, known as secondary coil. Transformers are used to step up or to step down voltages. Whether a transformer is a step down or a step up one is determined by the ratio of number of turns in the two coils. In a step-up transformer, the secondary coil has more number of turns than the primary coil. The voltage across the secondary coil is greater than the voltage in the primary coil. But the current in the secondary coil is less than the current in the primary coil. In a step-down transformer, the secondary coil has less number of turns than the primary coil. The voltage across the secondary coil is less than the voltage in the primary coil. But the current in the secondary coil is more than the current in the primary coil. Let us find a mathematical relationship between the number of turns in the coils and the voltages across them. Let us make three assumptions for simplicity. The current and resistance in the primary coil are small. There is no flux dissipation from the core, and the current output in the secondary coil is small. Let a voltage Vp be applied to the primary coil so that the alternating flux produced at a given time t is phi. If the secondary coil has ns number of turns, then the induced EMF or voltage in the secondary coil, epsilon s equals minus ns d phi by dt. This induced EMF is also the voltage. That is, epsilon s equals Vs, which means Vs equals minus ns d phi by dt. The alternating flux also induces a back EMF in the primary coil itself. This primary EMF is given by epsilon p equals minus np d phi by dt. But this induced EMF is the same as the voltage drop in the primary. That is, epsilon p is equal to Vp, or Vp equal to minus np d phi by dt, which means Vs by Vp is equal to Ns by Np. Assuming that the transformer is 100% efficient and no power loss occurs, the power output of the transformer must be equal to the power input. This can also be written as Ip by Is is equal to Vs by Vp is equal to Ns by Np. This equation gives us relationship between primary and secondary voltages and currents with respect to the number of turns in the primary and secondary coils. Well-designed transformers are usually 95% power efficient. Does the separating distance between the coils have an effect on the functioning of the transformer? Let us find out. We have a transformer with the primary coil connected to an alternating power supply and the secondary coil to a small light bulb. The AC sets up an alternating flux in the core. This flux induces an electromotive force in the secondary coil, which delivers energy to the bulb. Interestingly, if we gradually increase their separation distance, the brightness of the light gradually decreases to zero level. This is because, after a certain separation, very little or no flux gets linked with the secondary coil, and hence no current flows in the bulb. Usually, due to poor design or air gaps in the core, some magnetic flux from the primary coil is lost without linking with the secondary coil. This flux leakage can be minimized by winding the two coils over one another. As the wires used in the two coils have resistance, some energy is dissipated as heat in the wire. This can be minimized by using thick wires in high current, low voltage windings. Transformers also lose energy by way of eddy currents. These currents are induced in conductors when they are exposed to a changing magnetic field. Eddy currents cause heating in conductors and consequently power losses. Alternating magnetic field reverses the magnetization of the core of the transformer repeatedly. This phenomenon, which is attributed to a large extent due to some internal friction between particles in the iron core, gives rise to heat dissipation. Hence, materials which have low hysteresis losses are used as cores in transformers. Festivals are fun times, and Zach put a lot of effort to decorate this balcony. Oh no, the cinder has landed near the wire. He better blow it away. But how come his necklace got attracted to the railing? The balcony railing is behaving like a magnet due to the passage of electricity around it. This effect of electricity is known as the magnetic effect of electricity. Let's learn more about this effect. Since the 17th century, scientists have been looking for a connection between electricity and magnetism. But they couldn't find it. One day, when scientist Hans Christian Ørsted was demonstrating an electrical experiment, he accidentally found proof for the relation between electricity and magnetism. On his desk, along with the other experiment, was a magnetic compass lying close to the experimental setup. When he switched the circuit on, the magnetic needle in the compass instantly deflected. Ørsted was one of the scientists who was researching on the link between electricity and magnetism. When he saw the compass deflect, he immediately realized what was happening. He realized that when electricity passes through a wire, the wire behaves like a magnet. This property is known as the magnetic effect of electric current. Today, electromagnets are made using this property of electricity. Let's learn how to make a simple electromagnet. All you need is an electric cell, a long and thin insulated wire, a long iron nail, insulation tape, and a switch. Take the plastic wire and strip off a small portion of the plastic coating from the ends. Now, wind the wire around the nail. While doing so, leave a small length of the wire free from both ends. Use the insulation tape to fasten the free ends of the wire to the terminals of the electric cell. Now, complete the circuit by adding the switch. When you put the switch on, electricity will flow from the positive terminal to the negative terminal of the cell. As electricity flows through the wire, the iron nail gets magnetized and becomes a temporary magnet. Such magnets are called electromagnets. If the electric supply to the nail is cut off, it will immediately lose its magnetism. The strength of an electromagnet is directly proportional to the number of turns of the wire. The more the turns, the greater is the magnetic strength acquired by the electromagnet. Electromagnets can be very strong. For example, the large electromagnets used at garbage sites can easily pick up heavy pieces of iron, scrap, and steel. Electromagnets are used in various electronic devices. They are used in doorbells, computers, televisions, videotapes, and telephones. Let's see how the electromagnet of a doorbell functions. This is the circuit of a doorbell. When the switch of the doorbell is turned on, the circuit is closed. Electricity flows through the wire and the iron rod becomes an electromagnet. The electromagnet attracts the tiny hammer, causing it to strike the bell and produce a sound. When the hammer moves towards the electromagnet, it breaks the circuit and electricity stops flowing. When this happens, the iron rod loses its magnetism and the hammer returns to its original position. If the switch is still on, then the circuit is closed once again and the hammer strikes again. This will go on as long as the switch is on. This is Earth's magnetic north. Oh, can you see the compass? Let's put the table lamp on. Ah, now that's better. But wait, what's happened to the compass needle? It's showing a deflection now. Was this caused by the table lamp being put on? See there? Each time the lamp is put on, the compass needle deflects. Why do you think the compass needle deflects each time the table lamp is put on? When the lamp is put on, this wire begins to behave like a magnet because of the magnetic effect of electricity. This causes the compass needle to deflect. If this wire behaves like a magnet, then should it not have magnetic poles and a magnetic field? Just like a normal magnet. Let's find out by mapping the magnetic field lines around a straight conductor similar to this wire. First, let us insert this straight conductor through this cardboard sheet. Now, let us connect the conductor to a simple circuit consisting of a switch, a rheostat, ammeter, and a battery. The top end of the conductor is connected to the positive terminal of the battery. Let us sprinkle some iron filings on the cardboard and see what happens. Nothing happens right now because the circuit is off. Let us switch on the circuit and tap the cardboard sheet a few times. You can see the iron filings arrange into concentric circles around the straight conductor. What can we infer from this? On tapping the cardboard sheet, the iron filings arrange to form concentric circles. These circles visually depict the magnetic field created by the straight conductor. This is similar to what happens in the case of a bar magnet, when iron filings form a pattern around it. This indicates that the straight conductor is creating a magnetic field around it. Do these field lines have a direction? The field lines caused by a straight conductor have a direction. Let us verify this with the help of a compass. Observe the deflection. The north pole of the compass needle shows the direction of the field lines. The current flow is being reversed. The bottom end of the conductor is now connected to the positive terminal. What will happen to the deflection if the current flow is reversed? The deflection of the compass also reverses, indicating that the direction of the magnetic field lines has changed. Can you think of a simple way of finding out the direction of the magnetic field lines if you know the direction of the current flow? If you were to position your right hand in front of the straight conductor in such a way that your thumb points in the direction of the flow of current, then the direction in which your fingers curl is the direction of the field lines. Now, if you reverse the flow of current, you should be pointing your thumb in this direction. The direction in which your fingers now curl indicates the new direction for your field lines. This is known as the right-hand thumb rule. So far, we had kept the amount of current flowing constant. What will happen if the amount of current flowing is changed? Let us now keep the position of the compass fixed over here, so that the distance of the compass from the conductor is constant. Switch on the circuit. The compass needle deflects. Adjust the rheostat to reduce the amount of current. The compass needle shows lesser deflection now than before. So, the strength of the magnetic field decreases when the current decreases, and vice versa. What will happen if the compass is moved nearer to the straight conductor? Observe the deflection on the compass. Look at the deflection now, when the compass has been moved closer to the conductor. So, the magnetic field is stronger closer to the conductor.